Good morning. So this is the lecture that would have been on Wednesday, February 2/18. Let's go ahead and start about with what we've got going on this week. So there'll be no quiz Friday, tomorrow. No quiz Friday. There'll be a homework due. I'm getting this up on Thursday, so we'll not have the homework due on Friday. Let's have it due on um, Saturday. I've got a help session tonight. I'm going to say maybe help session tonight, and we'll maybe push it off. So maybe help session tonight. I know that's going to really help out attendance, but look for an email. All right, so I'm sorry I have this, how I'm sick is I have this fever. It comes back in the evening and I'm really feeling bad then, and I don't really want to do a help session if I'm above 100-degree fever. So maybe a help session tonight, look for the email. As always, feel free to reach out to me. If I don't have the fever tonight, I'll be in tomorrow for our regular lecture. And then I'll have my Friday office hours from 1:15 to 2:15 p.m. But if none of that stuff works for you, please reach out to me. I am happy to meet with you by Google Meet or in person, or we'll try it. We can make something work. So I have other times that are available, sort of, and we can make that sort of stuff work. Anyway, so before we get on to the lecture today, I want to advertise a chemistry club event. So Chemistry Club is having a model building event tomorrow at 6:30 p.m. So that might be something you'd want to do. Go build some models using Candy. It sounds like fun to me, and it might be something that's good to do before you start your other Friday activities. Having said that, let's go ahead and let's talk about catalysts. So we're going to start with catalysts today. Um, All right, there are multiple types of catalysts that we will talk about. We may also talk about equilibrium today. Not sure yet. We'll see. I'll talk about it today. It just may be a separate video. But so catalysts. What catalysts do is they speed up, or catalysts speed up reactions without being consumed. So essentially what happens is a catalyst gets used as part of the reaction, and then it is regenerated by the end of the reaction, and so it can participate in another reaction. Like reagents, the more catalyst you have, the more the reaction gets sped up, the faster it will go. And so if I pull this down here, we can go ahead and we can look at ozone as an example of this, or the mechanism for the destruction of Antarctic ozone. So a catalyst in that process is chlorine. You see we've got this chlorine right here. So it's a chlorine atom, right? So it's probably a chlorine radical. That chlorine, and so if we think about uncatalyzed, the reaction, for the uncatalyzed reaction, what we've got is we've got ozone. It's got to break down to make oxygen and a free oxygen. So it'll be an oxygen radical. And then when I say radical, I mean it has an electron that it has a free electron that isn't in a lone pair. So then that that oxygen radical can react with an O3, and then that can make two oxygen. Notice that the activation energy here is quite large. 93.1 kilojoules is a huge activation energy. It's a big activation energy. Let's just call it big. But over here, instead, we have a three-step mechanism instead of this two-step mechanism. For this three-step mechanism, what would happen here is that we'd have this chlorine that reacts with oxygen, and then it can make this chlorine oxygen molecule, And then we have oxygen, and that doesn't have a very high activation energy, nothing compared to the 93 kilojoules on the other side. And then here we have another, it happens again, same things. They've just shown it separately, they say for clarity. And then the last step here, I guess they decided it was too complicated to show all three elementary steps, but those steps are this. So if we were to look at these reactions, if we were in class, I'd ask you, hey, over here for this, just to review the sorts of things we're talking about, if we're looking at this uncatalyzed mechanism over here, what's the slow step? And you would hopefully tell me that this was the slow step. Remember that the speed of our reactions is determined by our activation energy for those reactions. And I'll review activation energy below. Hopefully you remember it, but if not, I'm going to review it below again. And then over here, this would be our slow step, but I'd be a little bit concerned about calling. I don't know. So remember I said that it's really unlikely that you'll have a bunch of steps that are all slow steps. 2.1 and 2.8 kilojoules are not that different. And so I wonder if we'd end up with something more complicated there than what we've talked about in class. And, you know, as you've probably gotten a feel, there's a lot of simplification. We often take more simple examples in class because this is general chemistry. And in a later chemistry class, you may learn how to handle more complex examples. Or you may not. That may be something that if you go on and you're doing high-end research in this that you would actually learn. So let's talk about what activation energy is here. So what we've got here is this is a general diagram. Let's say that what we've got here is we've got one pathway, we've got another pathway. It doesn't look like we've got an example of what these mechanisms would look like here, but before I talk about the mechanisms for these, I want to remind you, let's look at the blue pathway for the reaction. For the blue pathway, you can see that the activation energy is the difference between here and here, right? So that's our activation energy. And that's the amount of energy the system has to take on, or the chemicals have to take on to actually get up to our transition state, which we represent with a double dagger, to our transition state, so they can get over that hill and get from our reactants to our products. All right, so let's take a look at what this might be. So looking at this, we've got, I'm going to do it as R for reactants, and reactants goes to products, right? If we look at, we'll just say we have one of each, okay? So for this blue pathway, that's the uncatalyzed pathway, and what you get is our reactants have to get up and do some sort of transformation, twisting of the molecule or something, and such that we hit that transition state and go to products. One-step mechanism there. For our red path, we have an intermediate, right? So we have a catalyst. So let's call that, we've got a reactants plus our catalyst. As a biochemist, what I like is I like having our reactants stick to our catalyst. Okay, so that's a possibility of what might happen there. So we go from reactants to catalyst to make this reactant catalyst. And so here we'd have reactants, here we have products, right? And then here at this intermediate, I'd make this reactant catalyst thing. And then that reactant catalyst could break apart to make products plus catalyst. So notice that it's a two-step mechanism. If I was to add up the whole mechanism, the reactant catalyst doesn't show up in the reaction, and because it would cancel there if I add these two together, and the catalyst actually wouldn't show up in the overall reaction. But let's leave it in for the moment. And what you'll notice here is if we leave that in, what we do is I add up my catalyst plus my reactant. Let me actually do that red. I add it up and I've got my catalyst plus my reactant going to make product plus catalyst. So I start out with my catalyst. My catalyst gets consumed sort of in here, right? It's consumed and then it gets regenerated at the end so I can carry out another reaction and speed it up. How is my catalyst speeding up this reaction? Well, it has provided a different path, right? We have a different path in that we have a two-step mechanism, and that two-step mechanism has a lower highest activation energy, right? We've got an activation energy here, we have another activation energy here, right? But this is our big one, and so this would be our slow step for this reaction. And for our uncatalyzed pathway, the slow step, there's only one step, so it's the slow step. All right, but so hopefully you can see here, we have made this reaction faster by providing it a new way to go from reactants to products via the catalyst. So here's an example of that right here. There are things that we call homogeneous catalysts. All right, homogeneous catalysts are right there in the solution with everything else. So the catalysts are part of the solution. All right, remember that our solution can be either in liquid, which is normally what we deal with, or a solution can be a gas. And in fact, if we were to look up here, this right here is a homogeneous catalyst, this chlorine, because this is a gas. These gases are all mixed together. There's no real difference between them. There's not a difference in phase there. So here, catalysts are part of the solution. And this is an example. This is a good organic example of what would happen. We have a catalyst. Our catalyst here is this H+. We start the reaction with H+, and we end up with the reaction with H+. But what it's doing is in this two-step mechanism, it is giving us a new way to do this. And this could be, I don't know whether it is or not, but this actually could be a match for the diagram we have up above. Okay, our reactants here could be these guys, and these could be our products, because this is a two-step mechanism. If this was the one above, the slow step would be this one right here. And I really don't know what the reality is for this one, although I pulled this out of your book, so it may describe what it is in your book. But regardless, we have this example of a homogeneous catalyst here. These things are all dissolved in solution. It's not written, but this is going to be aqueous. This is going to be aqueous. Well, this is ethanol. Honestly, I'm going to say this is probably liquid. The H+ is probably dissolved in liquid ethanol. And so then we're going to have, this thing is going to be aqueous because it's not the solvent. The solvent is this ethanol. This is going to be aqueous. And then this is going to be aqueous. And then it looks like we make a little water. I'm going to call the water. Now I'm not sure what to do because actually our solvent is ethanol. You know what? I'm just going to erase all these. Because aqueous means in water. So if we're in ethanol, I'm not sure what I do with that. But we're not going to worry about it. So we have the H+ reacts with the O, sticks to this OH up here. It makes it easy for this OH to leave. And when this OH leaves, OH2 leaves, and then we also have an H+ is going to pop off. And we're going to get this double bond here. So the main point, sorry about it may have been a little confusing there with the aqueous bit. Pretend I didn't say it. But then the point here is this is an example of a homogeneous catalyst. The catalyst part is that it is in the reactants and in the products. It gets regenerated over the reaction. It speeds up the reaction by providing a different path. So we could imagine that the path provided by this two-step reaction is the red one up here. And then finally, it's homogeneous because it's in the same phase. This H+ is dissolved in the ethanol. So the ethanol is a liquid and the H+ is dissolved in it. They're the same. They're all right next to each other. Just like up above where we talked about the chlorine as a catalyst for ozone. There we had a whole bunch of gases mixed together. All right, we can have heterogeneous catalysts. All right, so heterogeneous catalysts. These catalysts are in a different phase than the reactants. I'll say products too. All right, so what's an example here? Well, here we have an example where we have the reaction actually above is what we've got going on here. So we have, no, we don't. This is an example of where if I look at what's going on here and I look at what 2 is and I look at what 3 is, we've got hydrogen, I'm going to guess that what we've got here is we're adding hydrogen to ethane. So this is going to be a C double bond C, a reaction here. And this is definitely a gas from what we're looking at here. And this is plus, we've got a palladium, which is a solid. All right, plus H2. And these guys go ahead, and the palladium, you could imagine the palladium sticking to both of these. I'll just make it like this. All right, so there we've got that. We've got an H2 down here, and then I'll redraw that again. Imagine this is the mechanism here. And you maybe hear my cat in the background. Yes, Sky, you are a mighty hunter. So here we have a reaction where we start out with ethene, which has this double bond between the 2 carbons. It sticks to the palladium, some hydrogen sticks to the palladium, and then the palladium holds them together and allows the H's to stick to or the H's to add to the molecule, and we lose the double bond to make the ethene. And that's actually what's shown here. This is an example of using palladium. Palladium gets used for this sort of stuff, and that palladium is a solid, is the important point here. It is a heterogeneous catalyst. The solid is in a different phase. In your this is not a reaction in your catalytic converter, but in your catalytic converter, I think you've got palladium, or maybe it's platinum, but you have one of these solid catalysts in the catalytic converter in your car. And what that catalyst does is it takes unreacted gasoline or gasoline products that are not fully oxidized to carbon dioxide, and it's going to take those products and it's going to make them fully oxidized, so that what you end up with is you end up with less toxic products being produced. Oxygen isn't great for the atmosphere, as you may have heard. It contributes to climate change. However, I just say oxygen, carbon dioxide is not good for, oxygen's great for the atmosphere. Well, I mean, the amount we have is great, but carbon dioxide is not good for the atmosphere. It contributes to climate change. But the other things like carbon monoxide is worse. It's really unhealthy. And there are some nitrogen oxygen compounds that are also pretty bad. So you want when you run your car, you want everything to fully react. You want it to make carbon dioxide and water. Let's just real quick look at that reaction since I'm talking about it. So gasoline is it's a mixture of things, but the main component is going to be, it's going to be made into a gas in your engine. The main component is this is octane, and that's going to combine with oxygen. That's not actually a reversible reaction because it's very spontaneous. And so it's going to make water plus carbon dioxide. I'm not going to balance it, but what you want to make sure is that you make this all the way to water and carbon dioxide, that you don't have some carbon that didn't get fully reacted and ends up being carbon monoxide. There's also some nitrogen compounds that form because you're in air. Okay. I'm going to talk about another type of catalyst here. These are enzyme catalysts. All right, and enzyme catalysts are biological catalysts that often greatly speed up reactions. So they're better than the catalysts we talked about above with, or let's say, under mild conditions. All right, so in other words, if we think about your catalytic converter, right, you've got a metal catalyst in there, your catalytic converter is super hot, right? Your body can't run, or biological organisms can't run super hot to get their reactions to happen. It has to be cool. The other reaction we had up above, we had to add a bunch of acid probably. I don't know how much acid this represents, but probably a lot that we'd add to make this go fast. So this ends up being H+. You get that from a lot of acid. Your body runs and biological organisms run at low or neutral pH. And so this is an example. This is an enzyme right here, acetylcholinesterase. This is found in the junctions between nerves. So we'll talk about synapses. So if I have a nerve cell up here, whoops, didn't leave room for my axon. If I have a nerve cell up here, it will have an axon, which is this long thing that the signal sends down, and then it will go ahead and it will talk to another nerve cell, which then will have an axon that can send the message down as well. This is a simplified view, by the way. But in between, when it needs to, it's got a gap junction here, and when it needs to send a message from this nerve cell to that nerve cell, what's going to happen is this compound here, acetylcholine, is going to go from here to here. So this cell says, "Hey, I'm excited," and so it's excited down this, and then it sends acetylcholine out into this junction, and then it excites this one, and then this one becomes excited. It sends a signal down its axon, and so you want that acetylcholine to go across from one axon to the other and have it send the signal. But once it's sent the signal, you don't want it to stay there. You don't want this acetylcholine to stay bound here and keep sending the signal. So you need to break it down, and that's where acetylcholinesterase is. It takes acetylcholine and it breaks it down. And the ACE might be your choice there. But what it's going to do is it's going to break this acetylcholine into two pieces. And it does this under neutral conditions. This is going on in your brain. It goes on other places as well, but let's say your brain mainly. Your brain is near neutral pH, and your brain is not like hundreds and hundreds of degrees Celsius, right? But or many hundreds of degrees Celsius like your catalytic converter would be. So that's what an enzyme is. In lab, I know you guys are doing Michaelis-Menten kinetics in lab. So you would have the Michaelis-Menten equation, which says that the rate, and I apologize if I may use slightly different letters than they did. I can't remember what I saw up on the board. But we've got a rate is equal to the maximum rate we could get times whatever the substrate concentration, which could also be called reactants. Let's call it reactants since we're Gen Chem, so reactant concentration over this constant called Km, which, well, I'll show you in a second, okay, times this constant called Km, time plus the reactant concentration. So we've got this nice equation that derives it. If you kind of don't want to know where that comes from, I'm not going to do the algebra because it's actually, when I teach my biochem classes, this is 30 to 40 minutes of algebra. And I think I'll completely lose you if I do that. So I've got an enzyme, but the model it comes from, I'm going to replace my substrates with the reactants. I've got enzyme plus reactant. I have an equilibrium to make an enzyme-reactant complex, and then the enzyme separates from that complex to make a product. Okay, and so I have a K, or K1, a K minus 1, and a K2. So then you've got, let's say, 30 minutes of algebra. All right, but this is one of those situations like where we talked in class where we had a fast equilibrium here and then we had a slow production of product here. And so then we could do the algebra to turn our enzyme reactant product here. We can turn that into things that are just actually, we go through and we just make it all about reactant. And that's all that appears in our equation. Okay. All right, so let's go. We've got a problem here. It says a reaction takes place through the three-step mechanism shown below. Write the overall net reaction for this sequence. So this is not really identify the catalyst. So it is a catalyst question. All right, so we're going to go ahead and do that. So I need to write the overall reaction for that. So if I'm going to write the overall reaction, I'm just going to add all these things up. All right. Now, what I'm going to do to make it a little bit easier on myself is I'm going to look for things that show up on both sides of the equation. Okay, and I can cancel those in writing the overall reaction. I can also tell you that in the first reactant here, we have H3O plus, right? And in the final product here, we have H3O plus being regenerated. That's probably our catalyst. So I'm just going to say right now, H3O plus is the catalyst. All right, so that's what you're looking for. Something in the beginning reactants and something in the ending products that's in both. All right, for the overall reaction, I'm going to go ahead and cancel those though, because they don't show up in both, right? I'm going to cancel water because I see another water over here. I've got a CH3OH2. I'm going to cancel those two. I'm going to cancel these two because they end up on, I'm seeing each one. My canceling is that if it's in the reactants and it's in the products, I can cancel it. All right, and then I think that's all I can cancel. So now I'm going to go ahead and write out what I've got left. What I've got left is on the reactant side, I've got CH3OH, aqueous. And then there's another CH3OH, so I'm just going to go put a 2 there. And that's all I see over here on the reactant side. And then on the product side, I see C2H6O, aqueous, and I also see H2O, liquid. All right, I think I've done that right, but the way I'm going to check is I'm going to actually see if I have the same number of all the atoms. So did I destroy any atoms from the left to the right? Do I have the same number on each side? So if I look here, I have 2 carbons, right? 2 times C here, 2 carbons, and here I have 2 carbons. Great. Here I have 2 oxygens, right? And I have an oxygen there and an oxygen there. So I have 2 oxygens. Great. And then, so now I have 4 hydrogens in this. This is methanol, by the way. In methanol, I have 4 hydrogens times 2 for 8 hydrogens. I have 6 hydrogens and I have 2 hydrogens. 8 hydrogens, 8 hydrogens. I think I did it right. Okay. All right, so that's how we could do that sort of problem. Now, what we're going to do is we're going to move on to a concept called equilibrium. Okay, equilibrium is the state where the forward and backward reaction are are operating at the same rate. So it's the state where, I'm going to restate that, where the concentrations of products and reactants are not changing. And so in this state, the rate of the forward reaction and reverse reaction are equal. All right, so this is a great example back down here. They have a reaction where HF is breaking up. So we're going to go ahead and use that in a second. But hold on to the forward and reverse reaction rates are equal. So let's pretend that's what's going on here. So what we've got is we've got HF, which is aqueous, is going to break up into, and this is going to be a reversible reaction. So I'm going to use my half-headed arrows here, and I'm going to make aqueous H plus and aqueous F minus, like that. Okay, so I'm going forward reaction, reverse reaction. And so my reactant here is HF, if we're using this reaction over here. It's a generic figure. And my products are going to be HF, or H plus F minus, okay? But what we're showing here is that when you see that, you start the reaction, the reactant HF starts getting used up, it starts getting used up, and then it kind of levels off, and you just don't end up with any change after some point. Same sort of thing with the products. It reaches equilibrium, right? This reaches equilibrium is this point right here, because that's where we have a flat line, and these things aren't changing. Okay. An important thing to note, and I'm going to write this down because it's super important and often people misunderstand this, is that the reactants, the concentrations of reactants and products at equilibrium are not equal. Okay? They are not equal, and as you can see in the example above, they are not equal. All right, there's a super unlikely chance that they might randomly be equal, but they are, just assume they are never equal. I think that'll serve you best. So they are not equal. And here you see we end up this reaction with more reactants than we end up with products, okay, which actually kind of reflects what happens with this acid up here. The H hydrofluoric acid. What is equal at equilibrium is the rate of the forward reaction and the rate of the reverse reaction. So let's go ahead and take a look at that right here. So what we have here is this is all written in this figure. And so we've got an equilibrium diagram here. You see that the energy of our products is higher than the energy of our reactants. So what that means is at equilibrium we will have more reactants than we have products because of the energy differences. And so what that means also is that if you want to do the forward reaction here, let's say this is a one-step mechanism, at least for the one-step mechanism, if we look at KF, okay, KF is going to be smaller, larger actually, right? Because we have KF is going to be determined based on this forward activation energy. I'm sorry. So KF needs to be smaller than KR, K forward versus K reverse. Okay, it has to be smaller because the rate is going to be slower, right? Because of a higher activation energy. And that will fall out of our Arrhenius equation, if you remember our Arrhenius equation from the last lecture. I'm not going to bring that in right now. So what that means is the reaction starts and the forward reaction is faster. So if we think about it, let me go and write this out. Reaction starts. And what we've got is, if we look at our two rate equations here, we've got our rate is equal to Kf, this is our forward reaction, times Hf, right? And we've got our reverse rate for our reverse reaction. This is our rate forward, our rate reverse, and that's equal to K reverse times H plus F minus. So at the start of the reaction, the concentration of HF is really high, right? Because that's all we've got. We haven't made any products yet. And the concentration of our H plus and our fluorine minus are both really low. So these get, even though Kr, let's make these like that, even though Kr is bigger, even though this is bigger than this, I've got hardly any reactants. So I multiply it all out and I end up with a small number for my rate. Here, even though Kf is smaller than Kr, I have a really large number for Hf, for that concentration, and so we have a fast rate. As the reaction goes on, this concentration goes down and these concentrations go up. And eventually we get to the point where as this concentration goes down, the forward rate slows down. As these concentrations go up, the reverse rate speeds up, and eventually we reach a point where the forward reaction is equal to, the rate of the forward reaction is equal to the rate of the reverse reaction based on the concentrations. And once we reach that point, things stop changing. Okay? We still have products being made and reactants being made. In terms of the forward reaction is still running, the reverse reaction is still running, but they run at exactly the same rate. And so we don't end up with a change in product concentration or reactant concentration, just like we see up here. Okay, the reaction is still going on right here. It's just equal in the forward and reverse direction. That's what equilibrium is. All right, so how can we express that? So we can actually express that using what we call an equilibrium constant. And that equilibrium constant is a big K. You notice that, remember how I've been making a big deal about big K, little k's for our kinetic constants. This is why I've been doing that, because for equilibrium we have a K again. Chemistry loves K's. There are K's all over the place. I don't know why. I can't fix it, because it's just going to continue to be that way. So you have to be used to all these K's. So what I can do though here is I can express what the concentration of these things is at equilibrium by writing a constant where I say the Kc here. Okay, so that C means concentration. Concentration, so it means we're in solution, not we're talking about a gas. We'll have a different thing we do for a gas, and that I think I won't include that in this lecture. We'll do it in the next one. But Kc is my concentration, and that's equal to the concentration of my products over the concentration of my reactants. All right, so in this case, I already did this. So remember at the beginning of, well, I guess it was at the beginning of my first term, I said that, so those of you who had me before have seen this, but chemistry is always products divided by reactants, or it's almost always, I should say. It's almost always when you have an equation, it's products over reactants or it's products minus reactants. Only very occasionally is it the reverse of that. So if you're later on, if you're taking some test for some big scary test for like med school or some other school, and you don't quite remember what to do, right? I don't know if they're going to give you the equations on those tests like I give you the equations on those tests. But if you're not sure what to do, make it products over reactants or make it products minus reactants.
don't do it the other way around, because that's usually not the way it goes. So anyway, what that's going to be is this is going to be the concentration of, but I just want to do this generally here, products over reactants for the equilibrium constant. Okay. So for Kc, it will also be the same for K. I think it's Kg, but I'll get to that when we get to that lecture. I was looking at it last night. I don't remember. All right, so what we can do is we can look at this reaction, and we can talk about, so here's our reaction we've been looking at, which is the dissociation of hydrofluoric acid. Turns out hydrofluoric acid doesn't dissociate much, and so what it says, what this tells us is that if we're going to have a K, that if H and F are really small, and HF is really big, then K is going to be very small, right? Okay, just want to think about the equation and what it tells us. Now, hydrochloric acid is a very strong acid. It almost fully dissociates in water. And so for this equation, H plus C, because most of it's here, is going to be very big. This is going to be very small, so K is going to be very large. All right. So the value of K, we could say that Kc greater than 1, or we'll just say K, okay? Because it's going to be the same for gas. Greater than favors K greater than 1 favors products, right? We're going to have more products. And K less than 1 favors reactants, meaning we have more reactants. Okay. So let's go on and let's look at, now that we know how to do equilibrium expressions, let's write 1 or 2 right here. I like the first one at least here, the second one here, because it actually has something I didn't talk about above. So let's actually talk about one more thing for equilibrium constants. Let's actually do the generic equation, because what the equation we have with HF doesn't have any, it only has one of each thing on each side of the equation. So what we can say is, let's say I have an equation that goes AA plus the little letters are the coefficients in front of the reactants in this case, and I'll do it for the products as well. CC plus DD. Okay, I've got all of those things going there. If I want to write this, let's say we're going to do KC, we're in solution. That's going to be products over reactants. But what happens is this coefficient, if it's a 2, it ends up squaring things. It ends up being an exponent in this reaction. So if KC is equal to C to the C to the little c times D to the little d over my reactants, which are going to be A to the little a over B to the little b, like that. Okay? Missed that earlier. Wasn't important for the things we were doing, but now it's going to be important. So that's generally how you write an equilibrium expression. All right, and that's why I like this particular problem, because we actually have I have some numbers that aren't 1. So let's go ahead and we'll do A and B here. So A, and you should go ahead and think about, if you think you got it, pause, do it, and start the video again. So then I've got my KC for A, this is for A, is going to be equal to products over reactants. So I'm going to have the concentration of C. It has a coefficient of 2 out front, so that becomes 2C squared over the concentration of A over the concentration of B. Okay, like that. And then for B, once again, pause. Now certainly pause and try to do B, and then start up again. So B is going to be, I've got a K, right? So it's going to be the concentration of K, and I have a 2 out front of the K, so that's going to be squared. And then J is my reactant, and J we're going to do to the third, okay, because we have a 3 out front. All right? And you could do C if you wanted. I'm not going to bother to do it here. And the answers are in the back of your book for these even number questions. All right, so here's another equation we could do. Let's go ahead and do this one. Okay, so here we're going to actually use numbers and solve for something. So at equilibrium, an aqueous solution of iodic acid has these concentrations, blah, 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 blah. What is the value of Kc for this equilibrium? Does it lie to the right or to the left? So in other words, when we say does it lie to the right or left, do we mean is it that direction? Is it product favored or is it reactant favored? Let's go ahead and solve this one. Once again, go ahead and feel free to pause. Try to do this on your own. And then once you think you've got it or whatever, you can start it up again and see how I did. All right, so what we need to do first is I need to write out my equilibrium expression here. And that's going to be the concentration of H+. There's nothing in front of that, so that's a 1 times iodate, I guess. I actually don't know what that polyatomic ion's called. Iodate, and then HiO3. Okay. So we've got these are our concentrations there. All of these things have a coefficient of 1 in, right? Because we don't have any number in front. So all these are going to, the exponents and all these things are going to be 1. Now I'm going to go ahead and I'm just going to put the numbers in. So I've got, these are all molar constants. This means molar. Okay, well it says molar too, but these concentration things mean no molar. And you want to be in molar. They assume that you're in molar for the equilibrium constant. So I'm going to have that molar. I'm going to put the brackets. Putting the molar inside the brackets is kind of redundant, but I'm going to do it anyway, just to be super clear. Huh, they're the same. Interesting. All right, and then my hydroiodic acid. Whoops. I want to actually write the number there. Okay, and so this really tells me the equilibrium lies to the left. Okay, this may not, well, we'll see if I get into trouble here in terms of my rule I gave you above. It was a simplification in terms of greater than 1 or less than 1, because I have two products and they're going to multiply times each other and make a smaller number. But you know, really, I have more products than reactants in terms of the concentration. So we're going to say left even before we see our answer, right? Because these concentrations are higher than that. Okay. Not always going to be clear, but if I ask you, I'll be careful with my examples. All right, I need to grab my calculator. .0203 times 0.0203 divided by 0.0024. Okay, and I actually get a number that actually does follow my rule up above, that my equilibrium constant here is going to be equal to 0.17. And there are no units that go in equilibrium constants in general chemistry. Informally, general chemistry is right. Go into biochemistry, we'll start putting units on them. You can worry about that then. But let's see, I had 3 significant figures, so I'll hold on. This bottom one only has 2 significant figures, so I'll do this. Okay, so that's my equilibrium constant. And what it tells me is because it's small, it's smaller than 1, it tells me that my reactants are favored, right? Reactants are on the bottom, so they make this smaller. So our thing about left up above was correct. All right, looks like I have 10 minutes left here. I'm going to go, since it's a video, I'm going to go over if I need the time anyway. So you can always pause. I would say don't get your hopes up, but you're not stuck, right? You can just pause, go get a sandwich, whatever. But I want to talk about solubility constants, okay? Let me look at solubility products is what your group calls them. So solubility products. All right, so what goes on here is there's only so much stuff. So if we think about dissolving solids in solution. We had, last term we had a bunch of things and we talked about whether something was soluble or not. But it's not really whether something's soluble or not, it's really whether it's really soluble or not very soluble. And a solid will always dissolve to some extent in a solution or in a liquid, but maybe not very much, or maybe a lot. So like sodium chloride or table sugar dissolves a lot in water. Lead chloride doesn't dissolve very much in water. And so we want to think about that. So solubility products are our equilibrium constants for let's say liquids, or let's actually say solids dissolving. That's really what we're going to be doing. It's solids dissolving in solution. All right, so if we think about this, let's go ahead and we'll just start with this silver chloride down here. Silver chloride is not very soluble in water. Whoops. There's two columns on this table. We're going to look at silver chloride. So what would happen with silver chloride is silver chloride is going to be AgCl. That's going to be a solid. And that's going to dissolve to some extent. We'll do this as an equilibrium. That's going to dissolve to some extent in water. Not very much. And I say not very much because I'm looking at the solubility constant. The Ksp is just an equilibrium constant for this reaction. Now, so what I can do is I can write my equilibrium expression that says that Ksp, okay, for this reaction, so it's the solubility product, is equal to 1.77 times 10 to the minus 10th. Oh, super, super small. So we're really favoring the product, or I'm sorry, the reactants here. Okay. All right, and that's equal to, and here we do something different. Okay. That's going to be equal to the concentration of Ag plus times the concentration of Cl minus. All right. And the reason why, and we don't write the solid, first off, I want you to think, what's the concentration of a solid? I've got a lump of silver chloride at the bottom of my solution. What's its concentration? Well, we really don't know how to calculate that. But so what we assume is that all of it that can dissolve is going to dissolve. And as long as you have solid left, you're going to saturate the solution with silver chloride. When I say saturate, I don't mean very much, but it's as much as silver chloride as will actually go into that solution. Okay, so you have as much as goes in. And as long as I have some solid around, if somehow I ended up with less of one of these, if I took some of those out by some way, that more would dissolve in until we got to a concentration or a set of concentrations that satisfied this solubility constant. All right. So so the upshot here is that whenever you write the rule right here. When you have solids or liquids involved, in a reaction, you do not count them in the solubility or in the equilibrium expression. Okay, when you write the K equals blah, 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 you don't include them. So for the solids, it's because we can't get a concentration for solid. You've got as much solid as you've got. As long as you have some solid sitting around, as much as can go into solution goes into solution, and as much as can go into solution is governed by whatever this constant is. Liquids, I'm going to give you a different explanation, but let's wait on that for 1 second. All right, so do we have a... All right, we're going to do this one because we just wrote that, right? It was 1.77. We'll do this one. We're going to do that one. So 1.77 times 10 to the negative 10th. Oh my gosh, that's so small. Is equal to AG plus times CL minus. Okay? And that's how I'm going to solve it. That's my equilibrium expression for this equation right there. For my equation up top, that's for B. Okay? And that would be KSP. The same sort of thing for calcium hydroxide. Calcium hydroxide, since we're just writing the expression, I'll have some KSP for calcium hydroxide. I'd look up above, and it was there, I saw it. And that's going to be equal to, I'm just doing this because I just drew the line, but I don't need to draw the line because on the bottom, the the reactant is a solid, so it drops out of the equation. And I write the concentration of calcium 2 plus times the concentration of OH minus. Okay? And because OH minus has that 2, I'm going to put that 2 there. All right, that's how I would write that. And if I had a reaction, I need to solve it. Let's see. Write an equation. Well, here's an example where we're not exactly using a solubility constant, but we're doing the same thing where we need to drop out our solids. Okay. So let's go ahead and do this problem right here. So write an equilibrium expression for this reaction at equilibrium. What is the concentration of Fe2 if Fe plus 2 if cobalt plus 2 is 2.7 micromolar? Okay. So first thing we're going to do is that remember these equations go for molar, all right? Sometimes you can get away with not changing your units, but there are times you can't, and so you will always be safest if you just put it in molar. All right, so I've got 2.4 micromolar. I'd look up at the top of my test and I'd see that there are 1,000,000 micromolar in 1 molar. And this would become 2.70 times 10 to the negative 6th molar. Okay? So I've changed their concentration from micromolar to molar. And you want to do that. Your equilibrium constants assume molar. All right, so then my equilibrium expression is Kc is equal to 4.38 times 10 to the 5th. And that's equal to products over reactants. So the concentration of iron plus 2 over the concentration of cobalt 2 plus. I should say 2 plus, not plus 2. Cobalt 2 plus. Okay, that's what we've got there. And then we actually had a number here for what was it? Cobalt 2 plus is 2.7 times 10 to the negative 6th molar under X. I don't know what that is. Hopefully this isn't confusing having the iron and whatever in the middle. I'm going to go ahead and multiply both sides by 2.7 times 10 to the negative 6th molar. Multiply this times 2.7 times 10 to the negative 6th molar. Okay. I've got to go ahead and erase those two. These cancel. All right, and just to make it, I'll rewrite it down here. X is equal to 2.7 times 10 to the negative 6 molar times 4.38 times 10 to the 5th. All right, kind of round those together a little bit, but let's go ahead and put them in my calculator. Looks like we're going to end up with something that's, in the 1 to 10 or something there. Let's see. Let me try and do math in my head. I'm going to call it 11, but I'm not sure I've got that. 2.7. No, I'm going to call it 1 or 2. 2.7 times 6 or whatever times 4.38 EE the fifth, and it's 1.1. There we go. I see it. I'm glad I revised my math in my head. Yes, it's 2.70. This was a 2.70 up there, so we're going to go ahead and give ourselves three significant figures. 1.8 molar. We actually did have a molar here. Okay, that would be our answer there. Oh no, wait, I'm sorry. Yeah, it is 1.8 molar. Such a big number. I'm just checking real quick. Okay, I'm going with that. Yep, all seems right with the world. 1.18 molar. I'm going with that. All right, a little over here in terms of the hour, but once again, you could stop and take a break, get a drink, get a sandwich. I want to talk one more thing about what happens with liquids, and I don't think we'll work a problem with it. Well, we might. No problems there. Here we can write an equilibrium expression that involves a liquid. So let's go ahead and we will do our explanation here. We'll write a quick equilibrium expression for it. So if I have another reaction where I actually have a liquid involved, and the liquid is actually reacting, I'm going to have to use their examples down here because I'm not thinking of one off the top of my head. But let's go ahead and take this one, okay? So we have something, both of these things are happening, A and B are happening in aqueous solution. So I've got this one we're looking at, right? I need to do an equilibrium expression. I told you that liquids drop out of the equation, okay? Just like solids do, although the explanation is different. I'll give you the explanation in a minute, but first I'm going to just go ahead and write out what the equilibrium expression should look like. So I'm going to have products over reactants. My product is C12H22O11. Oh, this is actually two glucose coming together to make a, what is that? I think it's a mannose. So the concentration of that, and then we have 2 glucose at the bottom. And I didn't write that out. It wasn't part of it because it's a liquid. And what's going on here is the liquid, it gets built into our equilibrium expression because the concentrations of this is going to be, this is going to be less than 1 molar, probably. This is going to be less than 1 molar, probably. That's usually what we see, right? Less than, unless we could even say equal to if we wanted to. But less than or equal to 1 molar. And the concentration of water in water, right? We have liquid and that's our solution. The concentration of water in water is 55 molar, right? So regardless of how much water reacts with these things, or how much water is produced in this case, it's not really going to change the concentration of our water. So the water, because it's a liquid, and it's so big as its concentration that it really doesn't change at equilibrium. And so it actually, its value gets built into the equilibrium constant that we don't write it. So I hope that's not too confusing. Let's go ahead and do the second one here. So here, once again, I'm going to write all the aqueous ones count, but my water doesn't count because there's not going to be, it's huge. Its concentration is huge, and its value will just get built in because it never changes. It's always 55 molar water. It will get built into the equilibrium constant. So I'm going to go ahead and write products over reactants. Like that. Those are my products, and my reactant is NH3. Okay? And I leave the water out because it's a liquid. All right, I am going to stop there. I'm going to go ahead and get your homework ready, and then I'll post this and send you an email about it. Hope you're all having a great day, and I'm hoping I'll get to see you tomorrow. Bye-bye.